I will I will begin with a word of prayer. You guys playing Hangman?
Yeah.
Ah, very nice. Classic. Is this attendance?
Yeah.
Are these the people who were here and left? A petition. Well, I guess I'm clairvoyant. I don't know. So, all right, let me begin with a word of prayer. Dear Father, we thank you for this day. I thank you for these students and them coming to get me for the remainder of class. Help us to make the most of the time we have left, Lord. In your name I pray. Amen. Okay, so you had a question about which one was it? So today, I'm supposed to tell you guys about equations of, like, I think circles and ellipses and hyperbolas. So
it was the binomial theorem.
Oh, binomial theorem. Sure, I can talk about that for a minute.
So, like,
what is it?
in parentheses, x minus 3 to the 5th.
Okay, so like if we want to do x minus 3, and I'll do x minus, let me do like x minus 7 just to make it slightly different. All right, to the 5th power? Okay. So, question is, what is that? Well, let's talk about just the generic form, a plus b to the 5th power. So the way this works, the binomial theorem, all it's really saying is you can use Pascal's triangle to write down powers like this. So Pascal's triangle is this guy. And there is a formula for this as well, but I don't guess we need the formula necessarily for this class at the moment. I mean, if we need the formula later, we'll get to it. I don't think we ever need the formula. There is a formula for these things, all right, that you might learn in a different, like a probability class or something. Anyway, so here, these are the coefficients you need for the expansion. So like, the way this works is we do a to the 5th, all right? That corresponds to this one. And then I do plus 5, a, and the way it works is as you go across, you're dropping the power of a by 1 each time. So we go 5a to the 4th, and then, so here we have b to the 0, and we increase the power of b. What comes next? 10. So then plus 10. All right, so here's the pattern. We drop a by 1 power, and we increase b by 1 power as we go across here. So you guys tell me, what's the next term? 10, all right, and then a to the what? B to the what? A squared, b what? Cubed, right? And then plus 5, b to the 4th, and then plus b to the 5th, okay? So this is like the binomial theorem in the n equals 5 case, okay? That's what it is. So when I talk about binomial theorem, we're just talking about this trick. So applying that to this, I would have what? I'd have like x to the 5th plus 5, x to the 4th times minus 7 plus 10 x cubed minus 7 squared plus 10x squared minus 7 cubed, plus 5x minus 7 to the 4th power plus minus 7 to the 5th power. Okay, that's your homework problem is pretty much the same, right? Except instead of 7, you got 3, and of course you want to clean it up, right? Put the numbers in your calculator and put it in standard form, and that's it. So.
And then just solve. Or rather than like.
Did the question just say to expand using binomial theorem?
Mm-hmm.
Yeah, that's it. Just clean it up is all.
So like with the other one, like it has 2x plus 1 in the parentheses, all I would do would just add 2x to the 5th. Like
So you had like 2x plus 1 to the what?
To the 4th.
To the 4th. Mm-hmm. So you think of this as being like a, think of that as being b, right? And yeah. Well, the 2x is a. So the way this one works is a to the 4th plus, so that one would be the next line up. So that'd be a to the 4th plus 4 a cubed b plus what's next? 6 a squared b squared plus 4 ab cubed plus, so it always bookends with like a to the 4th and b to the, So in this one, these terms for that homework problem are going to be like 2x to the 4th power, which is actually what? 2 to the 4th, x to the 4th, which is what? Which is 16x to the 4th. So that one starts with 16x to the 4th and it ends with 1 because 1 to the 4th is 1. Now, that one's small enough, like you could just multiply it out, but I wanted you to use the binomial theorem because it's easier. I just wanted you to know what it is all. Because like last time I taught college algebra, I never really mentioned the binomial theorem, and I felt bad about it afterwards. So anyway, kind of like I feel today about not coming to class for the first half hour. Yeah.
Also, just something like number 24.
So let me just steal your yowzers. Something like number 24.
Yeah.
Oh, okay. Yeah, this is a backwards problem. So problem 24. Let's see here. You're supposed to find B and C for which x squared plus bx plus c equals to 0 has solution. All right, so like, I'm going to make up something different, okay? X equals to, let's say, 5. And x equals to -3 there. All right, and then I'll do another one. What if you want x equals to 13 minus 2i? All right, so if I do those two, that should pretty well give you the idea. Okay, so the way to do these is the factor theorem. Guys, tell me what the factor theorem said. What did the... Did you already move it? Oh wow! But you're over there. So you got up and moved it?
Yep.
Well, thank you. All right. So the factor theorem says that there's a correspondence between zeros, right? Factor theorem says f of, say, r is equal to 0 only if what? Only if x minus r is factor, right? Of f of x. And here we're talking about f of x being a polynomial. So you see, if I have x equals to 5, that means I have, according to the factor theorem, that, well, this means that f, if I look at, think about f of x equals to x squared plus bx plus c, okay? That's the idea. So this says f of 5 equals to 0. This says f of minus 3 equals to 0. That's what it means to have a solution, right? When you plug the number in, you get 0. Well, the factor theorem says that this means you've got x minus 5 as a factor. This means that x plus 3 is a factor, right? So that means then you've got x squared plus bx plus c is in fact equal to x minus 5 times x plus 3. So what are b and c? Well, no, not that. So to figure out b and c, we just have to multiply it out. So this is like a reverse problem, yeah? So minus 5x, what'd you say?
I was gonna ask,
So if I multiply that out, I get that, right? So by inspection, b is equal to what? B is equal to -2, and c is equal to -15. That's how you work this kind of problem. Now the factor theorem is still true for complex roots, all right? And one of the theorems that I should have told you, and I think I mentioned it, but I don't know if I have really emphasized it that much, but if this is a solution, right? If this solves f of x equals to 0, right? So if this makes x squared plus bx plus c equals to 0, all right? When you plug that x in, what other x makes that is also the case? So this tells you also get x equals to 13 plus 2i. This is the conjugate solution. So remember, when we solve quadratic equation, they always come in pairs, right? The complex conjugate always comes with it. So if you have the one complex solution, you have the other. They always come in a pair like this. So now we can go back and we can use the factor theorem again. So we have x minus 13 plus 2i times x minus 13 minus 2i. That should be equal to x squared plus bx plus c. So what does that make? What does that make b and c? Well, we have to multiply it out. All right? And so when I multiply this out, let's see here. So it's helpful to think about x minus 13 as a unit. Think about these as a kind of a package deal here. Keep these together in your multiplication. It makes it easier to think about it that way. So I've got x minus 13 squared, all right? And then minus 2i times x minus 3 plus 2i times x minus, did I say 3? I meant 13. Minus 13, minus 13. And then plus 2i times minus 2i. So the really cool thing is that when you have complex solutions, they come in conjugate pairs, which means when you plug it in like this, the imaginary piece cancels. See that? And what's this over here? Yeah, negative 4i, which is? Remember, I squared is what? I squared is minus 1. So this actually works out. Yeah, minus a minus. Yeah, just 4, exactly. So that works out to 4. And this works out to x squared minus 26x plus 169 plus 4. 13 squared is 169. So cleaning this up, I think the one I gave you in your homework is not this ugly, is it? 183. Okay, so what is b? All right, so for this one, yeah, b is equal to negative 26. And c is equal to, 183 for this problem. Now, this is not the problem in your homework, but this is like the problem in your homework, okay?
And then I have
Yeah. The one with the part C, the one with the square root, we work the same way. Just do like x minus the root times x minus the root and multiply it out.
Okay.
Mm-hmm.
So for 25 on here, like you have c equals negative 3. Well, I'll just,
What?
I don't understand.
Okay, yeah, we'll work this in a second here. What was your question?
I'm sorry to say this, but where did the 14 come from?
14. Oh, that's a very good question. I think the answer is fall of man. So really, I can blame women. I mean, Eve. It's Eve. It's all Eve's fault. The short answer is that's a mistake. So thank you.
173.
So that's that. Yes, we're going to revise that to a 173. Very good question. Thank you. So yeah, sorry, I made a mistake. My bad. Maybe I made it on purpose for your learning. Let's assume that was the case. Let's see here. There's nothing to sneeze at. All right, let's see here. So you wanted to know what how to handle this problem 25.
Just one of them.
And so
Dr. Cook.
yeah.
If I do scared, sad, so I can There you go.
Okay. So so these problem 25 is slightly challenging given our current technology. All right, but so let's see here. Like part A, you're given that basically you're given that f of minus 3 equals to 0. Part B, you're given that f of minus 2 plus I root 3 is equal to 0. In part C, you're given that f of 1/2 and equals to f of 1/3 equals to f of 1/5 equals to 0. All right? So I won't work these problems, but I will try to give you a little bit of like a hint about it, okay? So what does that mean? So and you have the formula. When you look at the homework, it gives you the formula, right? But you're supposed to factor it. But you're supposed to factor it in the light of this knowledge, okay? So what does this knowledge tell you? Like the first one's easy. What does that mean if x minus 3 is there? This says, yeah, we can write f of x is equal to what? X plus 3, all right, times stuff. I don't know what the stuff is. You got to figure it out, right?
Yeah.
And
Is that stuff just the equation that they give you?
it's whatever you need. So what can you tell me the formula for a? X what?
X cubed
X.
minus 12x squared minus 79x minus 102.
Okay. So what does that stuff have to look like?
Well, would you be like an x squared? You get x squared.
Ah, yeah, very good. So you have understood that this is definitely x squared, right? And let's say plus, I don't know what the b is, but let me just put a b there,
Okay.
right? I don't know what it is, but I do know what comes next. What has to come last here? This stuff. What I have to, this times the constant term here has to give me 102 minus, right?
So divide that.
So what's 102 divided by 3?
34.
34?
No, don't trust it.
Don't try. Minus 34.
Okay.
But the minus, because it's a minus, so that I've got a plus 3 here, right? So you can figure this much out, right?
Yeah.
Now the question is, what do you have to make b?
How do you do that?
Well, there are various ways. Like one way we could do it would be just to, I mean, you guys follow this much? So in order for this to be equal to that, when I multiply it out, it has to match, right? So if you multiply this out, you can do that, right? You've got x cubed, right? Plus bx squared minus 34x plus 3x squared plus 3bx minus 102. And then you can collect terms, right? So this is really what? This is x cubed. What are my b? I got what? I got b plus 3, right? And for x, I've got plus 3b minus 34, if I haven't made a silly mistake, x minus 102. So in order for this to be equal to that, what do you need?
Can you repeat what you just did there?
I multiplied it out and collected like terms.
So good. Oh, I read.
Once we figure out what b is, we're almost done, right? So can you guys tell me, like, if this is how it looks, then what does this have to be? This has to match what? Right there, right? So what we have is b plus 3 equals to minus 12. So b is equal to what? Negative 15. So in this case, we have f of x equal to x plus 3 times x squared minus 15x minus 34. Now, whenever we have a quadratic, the question is, are we done, right? Can you factor that quadratic further? How do you decide? Well, can you? Yes? How'd you factor it? X minus 17, x plus 2. I think we have a winner. Yeah, because that gives me minus 17x plus 2x, which is giving me minus 15, and 2 times 17 is 34. So yeah, and there you go. My apologies, I seem to have worked problem 25 part A for you, but since you guys stuck around today, there you go. Like I said, this is a little bit challenging given our current technology. Part B, so like let me tell you a theorem. Here's a theorem. If f of alpha plus I beta is equal to 0, then x minus alpha quantity squared plus beta squared is factor. So this is the complex version of the factor theorem. This is what we actually, so like if you put this into practice in my problem 24 over here, you could see this at work. See, like look what happened. We had f of 13 minus 2i, right?
Yeah.
Equal to 0. What did we find after we multiplied that stuff out? We found x minus 13 quantity squared plus 4 was the factor. So if you don't want to go through what we did on the middle board, you can shortcut that by just knowing this theorem, which you can write on your formula sheet that I let you bring to the test. So anytime you have a complex root to a real polynomial, that means that you have a prime factor. So what does it mean? So like f of, let's put that into practice for part B here. What's part B? You've got what? F of minus 2 plus I root 3 equals to 0? Yeah? So what's that mean? That means that x plus 2, quantity squared, and here, so alpha and beta are just numbers, guys, all right? I don't want to use a or b because we use those for the quadratic formula, so I want to use something else, okay? Alpha and beta are they're just Greek letters, right? You guys like Greek, right? Okay, good. So my alpha is minus 2, and my beta is the square root of 3. If beta is the square root of 3, what's beta squared? What's that? If beta is square root of 3, what's beta squared?
3.
Yeah, just 3. So this, which we can multiply out, x squared plus 4x plus 4 plus 3 is plus 7. So this right here has to be a factor for your part B.
That's only one part. That's not like the answer.
Well, so what, you tell me, what was the formula for part? You tell me, just a second here, let me partition off this mess here. There we go. All right. So what, you go ahead, tell me what was the formula for part B.
X cubed plus 5x squared plus 11x plus 7.
So this, apparently, if you believe the theorem, and I do, is x squared plus 4x plus 7, right? Times what? Times something we don't know. But think, what has to go in that parenthesis? An x? Oh, did we already move over here? In the back? Did we already move over there?
Yeah.
Okay. Let's see here. So that has to. These are not allergies. These are laughing sneezes. I know laughing sneezes when I hear them. All right, anyway, so I'll allow it. So that has to be x, right? And by golly, that has to be, to multiply this out, the only way to get the constant is from the constant times the constant, right?
Yeah.
That forces us to put what here? How can I get a 7 from 7 times something?
1.
I have to add 1. Oops, I'm sorry, I factored it for you. Oops.
Okay.
So this one's actually easier. Now to be careful, we should multiply this out and like check. X cubed, I get a plus 4x squared here, plus another x squared, I get 5x squared. If I multiply this out, I get a plus 4x, plus 7x is 11x. So yeah, it works. And that's factored because you already know by the way you got to this that this is prime because it's formed from a product of the complex ones. So anyway, there's some help on 25 for you. I hope that helps. This is something that I meant to get to at some point, so it's good we did it now. But yeah.
So also in the packet it talks about circle, ellipse, and hyperbola.
Yes, let's talk about that. So circles, ellipses, and hyperbolas. What's up with that? So I was going to take my time and talk to you about this stuff like in a lackadaisical way for about 50 minutes, but here we are. So, circle. Aw, man.
That wasn't crazy if actually when all like this now.
So circles, ellipses, that's not how you spell it. I'll just say ellipse, circle, ellipse, hyperbola. This way I avoid the awkward plural form of these words, hyperbola. So, in a nutshell, here are their equations. The equation of a circle is something like this. X minus, let's say, x naught squared plus y minus y naught squared equals to r squared. This is a circle. Its center would be x naught y naught. All right? And it's the collection of all points that is what? Distance what? Right? What's the significance? So x naught, y naught's the center of the circle, right? What's the significance of r? It's the what? The radius, right? It's the distance, yeah? So a circle is the collection of all points equal distance from the center point. That's it. What this equation says, right? Do you guys remember what's the formula for the distance between 2 points? No? So the distance from xy to x naught, y naught is what? It is equal to the square root of x minus x naught squared plus y minus y naught squared. This is the distance formula. You take the difference of the sum of the squares of the differences between the 2 points in questions, and you take the square root of that. Essentially, it's from the Pythagorean theorem, right? If you square that, you get this. So what this is saying, this equation literally says the distance squared from the center point is the equation. I mean, so the distance squared from the center point gives you xy, which is on the circle. Every point xy is the same distance from the center point. And that's what defines a circle, okay? That's it. That's a circle. What's an ellipse? Well, an ellipse, a little bit trickier. Its equation looks something like this. X minus x naught quantity squared over a squared plus y minus y naught squared over b squared equals to 1. This is the equation of an ellipse. Ellipses are a little bit trickier in the sense that, you know, so let me make my life a little bit easier and just put x naught, y naught at the origin just to make it more friendly. What's the question? Is there a question? Did I do?
What's the guy?
That's just a label.
Okay.
Like if you wanted to, you could put x naught. Your book might have x naught, y naught equals to like h. So remember we used h comma k for the coordinates of the vertex. Yeah. Sometimes people will use hk for the center point. We could do that here too if you wanted. Just a label. Yeah, it's a fixed point. X and y are variables, but x naught and y naught are fixed point. They're characteristic of the ellipse. So if I put x naught and y naught at the origin, a lot of times we come up against that. So the picture for the ellipse, if it looks like it's at the origin, something like this, all right? So here I'm just putting x naught, y naught equal to the origin for the sake of you know, discussion. If that's the case, then what are the, see there are special points here and here and here and here. Can you tell me what those would be equal to? So, yeah, those would be x and y intercepts. All right, so the equation, the one I'm looking at right now would be x squared over a squared plus y squared over b squared equal to 1. All right, so if I put y equals, if I put y equals to 0, where am I? Think about it. Y equals to 0, where are you? that gives us x squared over a squared equals to 1, right? Which gives us x squared equals to a squared, which gives us x is equal to plus or minus a. So if the ellipse is based on it's based around the origin, you go, x goes from a over here to minus a. That's the x-intercepts where y is equal to 0. How about the y-intercepts? So that gives us y squared over b squared equal to 1, which gives me y is equal to plus or minus b. So these points would be like b, and down here minus b. So that's the significance of these variables a and b in the formula. They describe the so-called semi-major and semi-minor axes. Right? So an ellipse has two principal directions. And typically if those two axes aren't equal in like length from the center point, you have a minor one and a major one, right? And so depending on whether, so I've drawn the ellipse so it's like kind of vertically squished, right? Well, I mean, it's more vertical. That would be under the assumption that like A is smaller than B, right? B is bigger, so it has like a larger axis. If on the other hand, I had that A was bigger and B was smaller, then the ellipse would be kind of more squished like that, right? What happens when A equals B? No, when A equals B, it's squished the same way this way and that way. You're back here. So a circle is a special case of an ellipse when the semi-major and semi-minor axes are equal. So technically, circle is a special case of ellipse. So you could say this is when A is equal to B is equal to R, if you like, if you want to combine the cases. All right. So what's the next? Well, hyperbola. A hyperbola looks something like this: x minus x naught squared over a squared minus y naught squared over b squared equals to, let's say, plus or minus 1. If this is the pattern of the formula, then what you're looking at is what's known as a hyperbola. What's a hyperbola look like? So hyperbola, just let me be more specific here, because there's two different cases here. Let's look at the case x minus x naught squared over a squared minus y naught squared over b squared equals to 1. So to graph this, what it looks like, all right. So there's some kind of center point. I'll tell you what, to make this a little bit easier for you guys to, well, I'm debating whether or not I should put the center point at the origin again here. Yeah, I probably should. So for the sake of the graphing here, let me put the center at the origin again. So let's, just for the sake of getting used to this idea, let's put x naught equal to y naught equal to 0, okay? So in that case, we're looking at x squared over a squared minus y squared over b squared equals to 1, all right? So I'm saying the center, so-called center of the hyperbola is at the origin. So, all right, again, the same question. What are the x-intercepts? What are the y-intercepts of this? So we'll, if we look at y equals to 0, what do we get? If we look at x equals to 0, what do we get? So if you plug in y equals to 0, you get x squared over a squared equals to what? Equals to 1. So that tells me that x is equal to plus or minus a, right? So the x-intercepts are here and here. All right? So a comma 0 and minus a comma 0. How about the y-intercepts? We've got minus y squared over b squared equals to 1. In other words, this says that y squared is equal to minus b squared. What is the solution to that? Can you find a real number whose square is equal to a negative? You can't, right? That has no real solutions. What does that mean? No, there's no solution, right? Which means you need imaginary numbers, that's right. But for the sake of our graph, that means that there is no y-intercept. So this hyperbola does not cross the y-intercept. And in fact, what it looks like is something like this. All right? And it has what are called asymptotes. And the asymptotes are like this. They go through the center, which in this case is the origin, but generally speaking, it would be at another point, you know? My bad, but how do you figure out the equations of the asymptotes? Well, essentially, to find the equations of the asymptotes, you can look at x squared over a squared minus y squared over b squared, approximately, it's essentially equal to 0. Let me explain the logic of that. If x and y are like super big, then essentially that 1 is irrelevant. So to a kind of sloppy approximation, you get y squared over b squared is equal to x squared over a squared, which then gives you y is equal to plus or minus b over a times x. So these are the equations of the asymptotes. So this might have like slope m is equal to b over a. This one has slope m equals to minus b over a, and so that's the asymptotes.
Is this going to go with test?
Well, there's homework problems on it, so like those. So what was the what is the so let's look at the homework problem, yeah? What's the question?
So it says complete the square for both x and y and
Mm-hmm.
decide whether the given equation describes a circle, ellipse, or hyperbola.
Let's see here.
Point or null.
Okay, so
So you have like x
let me work the first one for you. So what's the equation?
x squared
Mm-hmm.
plus 2x minus y squared plus 4y
Uh-huh.
equals 0.
Okay. So what's the point? The last 10 minutes I've been explaining to you what your target is. All right. This is, if the formula looks like this, it's a hyperbola. If the formula looks like that, it's an ellipse. If the formula looks like this, it's a circle. The point of all those homework exercises is you can use completing the square to take what you're given and put it in one of these 3 formats. And so the way to do that is, you're like, well, we only completed the square in x before, right? But think about it. If you can do it in x, you can also do it in y. So how do we complete the square here? We got what? X plus what quantity squared? Yep, plus 1. And to be fair, I did what? I just added a 1, so I must take it away. Minus 1 squared, right? Which is just 1. And then I have minus, right? Y. Let's see here. Let me just do a little bit of pre-processing here. So that's minus y squared. I'm going to put some parentheses here just so we understand better. That's y squared minus a 4y. The reason I did that was just to emphasize we're completing the square inside the parentheses here, okay? That's what's going on. And so we've got x plus 1 squared minus 1 minus what? So complete the square on the y there. What do you got? Y minus 2, right? And then what? So that means we've added 4. So to be fair, we have to take away the 4. So minus 4 equal to 0. All right, so what are we looking at? We've got x plus 1 squared minus parentheses y minus 2 squared equals to what?
1. Right?
Well, yeah, add the 1, but we got 1 and then minus 4, right? So that's actually a minus 3 over there. Okay, so if I rewrite that a little bit, what I'm looking at then is, you know, minus parentheses x plus 1 squared divided by 3, plus y minus 2 squared divided by 3 equals to 1. So what are we dealing with here? What is this? Is it a circle? Is it an ellipse? Is it a hyperbola? Is it a point? Is it nothing? How would you get nothing? What would that be? If when you complete the square you get like a sum of two squares equals to a negative number, that has no solution. If you get the sum of the squares equals to just 0, that has just the center point as a solution.
Did you divide by -3?
I divided by -3, that's right. Yeah.
Why?
Because I want to put it back into this format.
Okay.
I mean, so this kind of format, like 1, and so, listen, so the thing is that this is, yep.
Because that's 1 rather than plus or minus 1?
Yeah. Well, you see, you could, I mean, I could put a 1 here, right? If I do that, then I need to put like a minus plus and a plus minus here. Maybe that's how I should write this. I don't know. Maybe you could. There's different ways of sorting through the. There's two different kinds of hyperbolas. There's the ones that open sideways like this, but that one is the opposite kind. See, because it's got the minus on the x and the plus on the y, which means when you go through this story time here, you get the imaginary equation, not for the x equals to 0, but for the y equals to 0, which, long story short, means that the graph of this is something like it's at -1, 2 is the center of it. Yeah, and it has, I believe, the slope. So the asymptotes, I think, are just y equals like their slope 1. Like this is the asymptotes, and this one opens vertically because it's the opposite pattern of the sines that we just went through. So its graph looks something like this. I think that's enough to answer the questions that I've asked you. This is a hyperbola centered at -1, 2.
So the -1, 2 is from the parts of the...
Yeah. So we still have Tuesday before the test, right? Yeah. So we should, you know, we can talk more about these problems Tuesday, obviously. And I do have your last quiz is graded, and it's in my office. If you want to get it, you're welcome to. If you don't want to get it right now, it's fine. It's all to you guys. Sorry I was so late.
Are you going to your office now?
Yep.
Okay.
Yep.
Mr. Cook.
Uh-huh.